So this lecture is going to look at acids and bases in water. And since in quantitative analysis, most of our situations dealing with acids and bases will be aqueous, so will be in water. So when we're dealing with acids and bases, we're typically going to be following the Bronsted-Lowry acid-base rules. Again, since we're dealing with water, we typically have protons that are being donated and accepted. If the term Bronsted-Lowry doesn't make any sense to you, go back and watch the first part of Chapter 8 video that goes through these definitions. So when we're looking at acids and bases in water and an H plus is donated, the hydrogen ion, the H plus, does not stay alone. Since we're talking about situations in water, water has two lone pairs of electrons, so 4 dots, and it's a neutral molecule, but it has the opportunity to accept a proton because of those lone pair electrons. So what we actually see happen is that water, H2O, becomes H3O plus. That H plus attaches to the H2O. So we call that hydronium ion. H3O plus is a water molecule with a proton that was donated by some acid at some point that bonds to it. So when we're looking at water and we're talking about acids and bases, and we say a proton is donated, it's actually the most correct to say that we're looking at hydronium ion, H3O plus. So the thing to watch out for, if we're looking at an aqueous solution, every time you see H plus, you can substitute H3O plus for that. So keep an eye out for things in your textbook, things in Sapling, even things like on exams or I talk about in lecture, that I try to use hydronium ion H3O plus since it is the most correct. But anytime you see H plus, as long as we're aqueous, with that little AQ in parentheses, you know that H plus and H3O plus are the same thing. Okay, so since water is our solvent pretty much all the time in lab, we have to see how water handles serving as either an acid or a base. So when we have pure water, or just water in any situation, it will do an auto-ionization. So basically it goes to equilibrium with one water molecule acting as a Bronsted-Lowry acid and the other one acting as a Bronsted-Lowry base. Okay. If we have water in the presence of another chemical, it's amphiprotic, which means it can serve as either an acid or a base because it's got protons it can donate. It has an H pluses that it can donate. It also has lone pair electrons where it can be accepted. But if we're looking at just straight water, so two water molecules that are alone, they do react and go to equilibrium, where one water molecule serves as the acid where it donates an H plus, so it becomes hydroxide ion, and the other water molecule accepts that H plus because becoming hydronium H3O plus. So since this is an equilibrium process, we can apply all of our lovely equilibrium rules to this, which means we can write an equilibrium constant. So it's always products over reactants, right? When we're looking at a capital K equilibrium constant, you see I have H3O plus molarity times OH minus hydroxide ion molarity, but then I don't have the water molecules in the denominator. That's because if you think back to how equilibrium constant expressions are formed, if you have something that is a pure solid or a pure liquid, they are equal to 1. So really both of those water molecules on the reactant side, it's like they're both 1s. So it's H3O plus times OH minus over 1 times 1, which 1 times 1 is 1. Over 1 doesn't really give us anything. So this is our simplified version of the equilibrium constant expression for water. Since this is unique for water, instead of a Ka or a Kb, which are the subscripts we see often with equilibrium constants, we see Kw, W for water. Okay. And at 25 degrees Celsius, the equilibrium constant for water is 1.0 times 10 to the negative 14th. Equilibrium constants are temperature dependent, which means if we have water at a different temperature other than 25 degrees Celsius, that constant value will change because, again, they're temperature dependent. But we're going to, for the most part, pretend like all situations we come across are going to be at 25 degrees Celsius. So we're going to treat this 1.0 times 10 to the negative 14th as a true constant that's always going to be equal to Kw for us, just to make our lives a little bit easier. But to be completely accurate, this is the equilibrium constant only when we're with a solution that contains water at 25.0 degrees Celsius. Okay, so if we have a perfectly neutral solution of water, so it's only water, it's neither acidic or basic, that would mean that the hydronium ion and the hydroxide ion concentrations are equal, because for every one water molecule that dissociates, it donates one H+, which becomes H3O+, and what is left is OH-. So every time one water breaks up, we get one H3O+ and one OH-. So their concentrations should be equal. So using that and then substituting it into the equilibrium constant expression, okay, I'm going to let H3O+ stand for X and OH- stand for X, which is where what we get here, since H3O+ and OH- are equal, only in a neutral solution of water. Again, X is going to stand for the molarity of each of them. So really I have X squared equals 1.0 times 10 to the negative 14th. All I have to do is square root both sides to solve for X. And what I get is 1.0 times 10 to the negative 7th. So if I have a neutral solution of water, the hydronium and the hydroxide ion concentrations should be 1.0 times 10 to the negative 7th. Again, this is actually only true at 25 degrees Celsius. Okay, so if we got neutral solution of water, 1.0 times 10 to the negative 7th is the molarity. Well, when we're dealing with acids and bases and we're trying to quantify the acidity or basicity of something, we typically use the pH scale. And since oftentimes our hydronium ion concentration is actually a very small amount, the pH scale is easier to use than, like in this past example, 1.0 times 10 to the negative 7th. Negative times 10 to the negative 7th is a very small value. So the expression on how to convert the concentration of hydronium ion into a pH value, which pH values are unitless, we just take the negative log of the hydronium ion molarity. So those brackets, they're signifying the unit molarity. It has to be molarity. You can't plug in moles, grams, I don't know, parts per million. It's got to be molarity. And for the pH scale, it has to be hydronium ion. So if it's been a little bit and you need to dust off those rules for significant figures in logs, go back and check out chapter 3. So we're going to be following our sig fig rules. So we're going to practice using this equation with a neutral solution. So based on the molarity that we solved just in the last slide, we want to calculate the pH of a neutral solution of water. We're just going to take the negative log of the 1.0 times 10 to the negative 7th. And just a reminder on sig fig rules, when you're dealing with logs, the number of significant figures inside of the number that's being taken as a log. So in this case, I'm looking at the sig figs of 1.0 times 10 to the negative 7th. So 2 significant figures. That's the number of decimal places we get for our answer. So 7.00. So my calculator just said 7. I added the 2 decimal places to the right of the decimal point due to significant figures. In reality, you have never seen a pure neutral solution of water. Even our deionized water in our beautiful blue squirt bottles, there are a lot of ions have been removed, but it is not pure H2O. To get a pure sample of water with the pH of that's right at 7.00, it would have to be distilled 42 times. And we're not going to do that. You're not going to do that in organic. I've never seen water that pure. So having a neutral, saying that water has a pH of 7, it's not wrong, but it's not realistic either. You're not going to find water that has that exact pH. So if we're living in the world of 25 degrees Celsius, the pH scale, obviously if we've got neutral solution of water, the pH is 7, we just calculated that. So that's the dividing line between the acidic and basic side. So everything with the pH value less than 7 is acidic, and everything with the pH value greater than 7 is basic. And you'll see on this scale that the pH scale is not just limited to 0 to 14, which may be what you've seen in the past. It's whatever you calculate it to be based on the hydronium ion concentration. That gets down to a little bit less than -1, you can go up to 15. Okay. So the further away from 7 you are, the stronger. So the lower the pH value, the more acidic. The higher the pH value, the more basic. So just real quick practice with that pH expression, but this time we have a given pH value and we're trying to solve for the hydronium ion concentration. So we're using the same equation, but we're just going to be solving for a different variable. So I go ahead and plug in 4.30. And I'm trying to isolate the hydronium ion, the H3O plus molarity. So I'm going to divide both sides by -1, and then do the inverse of log, which the inverse of base 10 log, log, is 10 to the power of. So I divided both sides by -1, making it -4.30 equals log of hydronium, and then take 10 to the power of both sides. So now I need to plug into my calculator 10 to the power of -4.30. And that will give me my molarity of the hydronium ion. Now again, think in sig fig rules. When you're using 10 to the power of, you're looking at the number of decimal places in that measurement. So 4.30 has 2 decimal places to the right of the decimal point. So 2 decimal places. That becomes the number of significant figures in your answer. So 5.0 times 10 to the -5th. That has 2 significant figures because 4.30 has 2 decimal places to the right of the decimal point. The unit of this 5.0 times 10 to the -5th is molarity, and those brackets are telling you that. So sometimes we are not given the concentration of hydronium ion, but of hydroxide ion. So for example, if we had a strong base, that's what we would see. So if I have a hydronium or hydroxide ion concentration and I want to solve for the pH, I could go back and apply it to our Kw expression. So that's what I did here is I substituted the value of the hydronium ion concentration in the hydroxide ion concentration, sorry, into that value. So I'm going to divide both sides by 2.50 times 10 to the -7. That's where I got this value. And then to become a pH, negative log, and I get 12.398. So this solution is basic. The pH is above 7. So just practice using our pH equation. This is just for funsies. So this is just an image taken out of our textbook showing you the pH value of more common household type of things. Nothing really to memorize, but just some things that might be interesting. My favorite is that the theoretical pure rain, so rain that is not considered acid rain, has a pH of 5.6, which, if you think about this pH scale, pH of 5.6 is acidic. So acid rain, which is a real thing, it's just that acid rain is just more acidic than regular rain, but all rain is always acidic. So it should be, instead of like acid rain, like more acid rain, but you know, whatever. They don't ask me these things. So moving on, we're gonna see several other P scales, other scales like pH, but that are not based on the hydronium ion concentration. So one we see a lot is POH. You'll see the same pattern. If you see a lowercase p in front of something as a scale, you just take the negative log of whatever that is. So POH, negative log of OH minus. If I want to do like P calcium, negative log of calcium. It's just the unit is going to be molarity. Okay. pKw, the negative log of Kw. We'll see pKa, negative log of Ka. Okay. But using the these definitions, that equilibrium constant expression, Kw equals hydronium times hydroxide, if I just take the negative log of that entire equation, what I end up with is pH plus POH equals 14. This gives you a second way to convert to pH if you're given hydroxide ion concentrations, and this is actually the way that I prefer to do it. So as we get into the calculations, the real calculations with acids and bases with this chapter, we're going to see that pH plus POH equals 14 expression come up a lot more often.